Welcome back, software engineers, tech leads, and product managers. Today, we're exploring a truly fascinating blueprint for agentic programming and code orchestration. Think of what we're about to look at as, well, the digital equivalent of an orchestra conductor. In this explainer, we'll be walking through a React-based workflow orchestrator. It's a system that brings modular, independent pieces of code together to perform a complete symphony of automated tasks. As you'll see, it is an awesome deep dive into how a smooth front-end user experience can perfectly mirror complex back-end execution logic.
Okay, let's dive into this. Here is our top-down blueprint that's going to guide us today. We'll start with the visual flow canvas, then check out node types and configuration, followed by schema mapping and transformation, the DAG execution engine, and finally overlays, logs, and output.
So, to ground our explainer right off the bat, let's define exactly what it is we're looking at. Derived directly from the source code, this workflow orchestrator is essentially a node graph execution engine. It relies on directed acyclic graph, or DAG, logic to let users visually connect triggers, map out data schemas, and automate execution steps. If you imagine the React Flow canvas as our performance stage, the individual nodes are our musicians, each just waiting for their specific cue to play their part.
All right, moving into Section 1, the Visual Flow Canvas. Let's look at the UI setup environment.
Our primary interface is built right into a file called canvasoverlay.tsx. It constructs this really powerful main control header that allows you to instantly load preset blueprints, like an HTTP pipeline or a webhook alert. You can also import raw N8N standard JSON configurations to instantly populate a massive, complex workflow right onto the stage. With log toggles, clean JSON exports, and a handy Control+Enter shortcut to trigger runs, it's absolutely entirely designed to reduce user friction.
Now, what's really interesting about this slide is how the application dynamically styles connection edges based on real-time execution states using Flow Canvas TSX. Inner edges that are mapping schema keys, they get this active yellow dashed animation. But when a node successfully executes and passes its data forward, that edge visually transforms into a thick, animated green line. You aren't just sitting there reading terminal logs, you're literally watching the data flow and succeed in real time. And that status-driven visual storytelling, it continues directly with dynamic node status badges. The user interface is constantly pulling the Use App Store execution state to reflect what each and every node is doing at any given millisecond. The status shifts smoothly from idle to running and then to either success or error. It gives you immediate, glanceable context right on the canvas.
Let's shift gears to Section 2, Node Types and Configuration. This is really the brains of the operation.
Take a look at this breakdown of the node config map. What's brilliant here is the shared component architecture. Whether you're dropping in a manual trigger, an HTTP request, a set map for transforming data, or a code transform block, they all actually share the exact same universal node component under the hood. But to keep things clear for the user, they utilize entirely distinct UI badges, icons, and colors, like emerald for your triggers or indigo for actions, so you instantly know their specific role in the orchestra. Now, when you want to fine-tune one of these nodes, you just click on it, which triggers the node details drawer.tsx file. Clicking a node opens up a highly granular configuration form, and it's mapped exactly to the required JSON schemas for that specific node type. A manual trigger gives you a simple JSON payload form. An HTTP request prompts you for methods, URLs, and headers. A code transform node, it actually provides a full JavaScript code editor. It's completely context-aware, so you only see the inputs you absolutely need to see.
Which brings us to Section 3, Schema Mapping and Transformation. Let's look at how we handle data.
Let's break down exactly how this builds transformation logic, mechanically speaking. Step 1. The UI parses mock presets and introspects the incoming payload so it can dynamically infer the source JSON structure. Step 2. It compares that incoming data against whatever target JSON schema the user has defined. And Step 3. It generates the actual transformation mapping rules. For instance, it might take an incoming field like @JSON.id and intelligently map it directly to a target field like user ID.
But it gets even better. To make workflow creation completely painless, there is an auto-generate mappings from schema function built right in. The system looks at the incoming variable keys, checks out the target schema properties, and automatically links the matching data fields for you. It literally does the heavy lifting of data transformation, saving you from doing all that tedious manual mapping. Moving into Section 4, the DAG execution engine. If the nodes are the brains, this is the orchestrator's brawn.
The moment you hit that Run Workflow button, a function called Run Workflow Execution steps up as our conductor. It reads the topological sort of the directed acyclic graph and orchestrates execute single node for each active block in the precise mathematical sequence required. And while this is happening, those use abstore state modifiers track the exact lifecycle of every single block via commands like record node start and record node finish.
So the crucial point here is how the system validates a clean run. When everything finishes up perfectly, a very specific success message is triggered from global overlays.tsx. Cons DAG execution completed cleanly with 0 errors. This is the ultimate validation that the underlying topological sort and the sequential execution succeeded flawlessly across your entire graph.
And honestly, that 0 right there is everything. The execution engine tracks performance meticulously. It's tracking your total execution duration down to the millisecond, and it tracks the error count down to exactly 0 in a clean run.
Let's wrap up with Section 5, Overlays, Logs, and Output. Let's see how the system reports the aftermath of an execution. Through the Execution Log Viewer, you get this really clean, step-by-step chronological trace of exactly what the engine is doing. It builds a timeline right in a side panel, starting with the trigger node executing at 0 milliseconds, then moving into the processing of action nodes while they are in their running state, and concluding by logging the final success or error output.
The visual language here is super stark and totally intentional, driven by the CSS logic in the viewer. A clean, successful execution renders as crisp, emerald text on a dark slate background. But if there's a runtime halt, you are immediately visually alerted by rose text on a rose-tinted background complete with a node execution failure banner. You literally cannot miss it.
And this brilliantly illustrates what I think is the core technical secret of the whole orchestrator, the inode execution data interface. This is the standardized payload structure that gets passed between every single node in the graph. By forcing the data format into a standard JSON array of objects, completely disparate agentic blocks like an HTTP request, a custom code editor, and an email sender can communicate with each other flawlessly.
Once the workflow finishes up, the success modal pops up to capture and display this final payload. It takes that raw, complex code data and translates it into clean, human-readable metadata badges. You get to see the name of the final output node, its specific type, the total execution duration in milliseconds, and exactly how many total items were produced.
Now keep in mind, this entire orchestration state, the visual layout, the specific node configurations, the mapping rules, all those connections, it's not just stuck in the browser. The import and export JSON lifecycle perfectly serializes your nodes and edges arrays. That means you can perfectly save, share, and instantly restore these massively complex graphs whenever you need them. We've just seen how effectively this DAG engine orchestrates current programming logic. But it leaves us with a pretty fascinating question to think about. As visual orchestrators become the standard, how might these modular, agentic programming blocks evolve to handle incredibly dynamic logical loops and true AI-driven branching in the future? The foundation is clearly built. It seems autonomous orchestration is next up.